Very good morning, my dear students. Let us start with today's topic, that is continuation of previous topic, that is telecommunication traffic. So we were discussing about telecommunication traffic. In the last class, we discussed about the introduction part, what actually telecommunication traffic means, what are the units of traffic. We have discussed some of the definitions of telecommunication traffic, that is busy hour, congestion, grade of service. Okay, and we discussed some 4 5 problem examples also, and how the traffic measurement is done, what are the parameters we are going to consider. Okay, and today we are going to discuss with the mathematical models and last call system. Again, we have some problems and derivations in this section. So as I suggested in the last class also, kindly keep the calculator with you. If not, kindly install app from Play Store or from the Android, or if you're using Apple, means from Apple Store, you just download a scientific calculator and keep it ready to solve the problems. So let us go back to the actual topic. So today let us continue with this topic, that is state transition diagram of n trunks. So here you need to recall your memory from information theory and coding, what we discussed, that is probability theory. So state transition diagram, that means, so if there are n number of states, how the transition takes place from one state to another state. Here the same concept is used for telecommunication traffic by considering n trunks, that is n number of trunks. So let us consider for a group of n trunks for number of calls in progress varies randomly as discussed being of this chapter. This is an example for birth and death process. The number of calls in progress is always between 0 and n numbers. If thus it has n plus 1 state, its behavior depends upon the probability of the changes from each state to one above and to the one below it. Such process is also called as Markov chain. So if you recall your memory in information theory and coding in 5th sem, we discussed about Markov chain, how it is going to operate, right? In a similar fashion, it is going to, so in the same fashion it is going to operate. So this is a state transition diagram of n trunks. So this is state 0, this is state 1. Similar fashion, there is state j, state k, and this is n minus 1 state, this is n state. So here you can see the transition from 0 to 1. This arrow mark indicates probability of 0 1. If there is a transition from 1 to 0, so the probability will be p of 1 comma 0. So this is indicated as p of 0, that is probability of state 0, probability of state 1. This is a transition probability of state 0 to state 1. This is a transition probability of state 1 to state 0. In a similar fashion, we have the transition probability of state j to k, and this is the transition probability of k to j. Fine. So where p of j is a probability of state j and p of k is a probability of the next higher state, that is k. P of j comma k is a probability of state increasing, that is transition from j to k, and similarly the probability of uh, decreasing from k to j is nothing but p of kj. And we know the state probabilities, that is p of 0, p of 1 till p of n are called state probability, and the conditional probabilities are p of j comma k, p of k comma j are also called as transition probability, which I told earlier. Okay, in Markov chains, if these statistic equilibriums, these probability do not change, the process is said to be regular. Okay, so consider a very small interval of time, that is delta t, starting with the time t. Since the delta t is very small, the probability of something happened during it will also be very small. The probability of two or more events during delta t is therefore negligible. The event which can happen during delta t are thus follows: one call arriving with probability, that is p of a, one call ending with probability p of e, and no change with probability 1 minus p of a minus p of e. So I'll repeat: the event which can happen during delta t, that is small, which will be one call arriving with probability p of a, one call ending with probability p of e, no change with probability 1 minus P of A minus P of. So next, we know that A is equal to CH by T longs. So the amount of traffic is equal to C into H by T. So we already discussed this in the last class. A is equal to C when H is equal to or directly proportional to T. A is equal to C longs. Okay. Thus the mean number of arrival number of time with respect to delta T is A into delta T by H. Delta T is very small, we already discussed, so it will be less than 1, which represents the P of A of call arrival during delta T. Therefore, P of Jk is equal to P of A, which is equal to A into delta T by H. If the mean holding time in H and the number of calls in progress is K, one expects an average of k calls to end during a period of h. The average number of call ending during delta t is therefore we can keep it as k into delta t by h. Since delta t is very small, what we have discussed till now, so k into delta t by h is also much less than 1 and represents the probability that is p of e of the call ending during delta t. Therefore, p of kj is equal to p of e, which is equal to k into delta t by h. If the probability of j calls is in progress at the time of t is p of j, then the probability of the transition from j to k busy runs during delta t is p of j to k is equal to p of j into p of a, which is also equal to p of j into a into delta t by h. So kindly remember the expressions. If the probability of k calls at time t, that is p of k, then the probability of transition from k to j is busy run during delta t. Therefore, probability of k to j is equal to p of k, p of e, that is p of k into k delta t by h. The assumption of static equilibrium requires p of j to k is equal to p of k to j. Otherwise, the number of calls is in progress would steadily increase or decrease. Okay, that means we need to assume the static equilibrium in order to show the transition probability. Otherwise, the number of calls in progress will be getting increased or decreased. So thus we have from the equation number 4 and equation number 5, we have, since we are equated both, let us equate both. So P of k into P of k into delta t by h. So both delta t by h will cancel. So we are left with P of k, and this k will come to denominator. So we are left with a divided by k into P of j. Hence, P of 1 is equal to a by 1, P of 0, P of 2 is equal to a by 2 into P of 1, which is also equal to a square by 2 into 1 into P of 0. Similarly, in general, if you write an expression that is P of x is equal to a to the power of x by x factorial into P of 0. This is very important, as we already know that we have used this formula for solving a problem. The assumption of pure chance traffic implies a very large number of sources. Thus, x can have any value between 0 and infinity. Their sum of probability must be unity. Okay, the x can have any value from 0 to infinity, and their sum of probability should be unit. That is, unity means 1. So 1 is equal to summation of x is equal to 0 to infinite p of x, which is equal to summation of 0 to infinity a to the power of x by x factorial p of 0, which is equal to e to the power of a into p of 0. Okay. So thus, if a call arrivals have a Poisson's distribution, so does the number of calls is in progress. This requires an infinite number of trunks to carry the calls. So last call system. L-longs determines the grade of service of a last call system having n trunks when offered traffic A. Okay. Its solution depends upon the following assumptions. So this last call system is one of the important topic. They may ask you for 10 marks a derivation. It's a derivation. So as we know that in telecommunication traffic, the unit of traffic is measured in terms of Erlang, that is indicated by capital E. So these are the four assumptions we need to make for lost call system. One is pure chance traffic, we discussed already. Static equilibrium also we discussed, but these two are new one. There is fully availability and calls which encounter congestions are lost. So here this is a diagram which says that the traffic offered in Erlang's for incoming trunks. These are n outgoing trunks. As we know that there are four assumptions. In the first assumption says that the pure chance traffic, the call arrival and call determinations are independent random events. So second assumption, before going to second assumption, pure chance traffic, here they say that the call arrival and call terminations are totally an independent random event. Both are not dependent, both are independent, and they are also a random event. And static equilibrium, it implies that the probability do not change. That means whatever matters, the probability will not change. Fully availability. Fully availability means that the every call that arrives can connect to any outgoing trunk which it is free. Fully availability means every call that arrives can connect to any outgoing trunk which it is free. That is nothing but fully availability. Next, call that encounters congestions are lost. So that means if there is a congestion in the medium, if any call occurs, that call will be lost. So here the last call assumption implies that any attempted call which encounters congestion is immediately cleared from the system. Okay, so these are the four assumptions, that is pure chance traffic, static equilibrium, fully availability, and call that encounters congestion are lost. So now if there are x calls is in progress, then the equation will be, that is p of x is equal to a to the power of x by x factorial into p of 0. This derivation, the formula we discussed right now, so which is very important for problem point of view also. However, there cannot be a negative number of calls, there cannot be more than n number of calls, then we may know that x can vary from 0 to n. Therefore, the summation of 0 to n p of x is equal to 1, that is unity. Similarly, the summation of 0 to n a of x by x factorial p of 0. Hence, p of 0 is equal to 1 divided by summation of 0 to n a of x by x factorial. By substituting the above equation in equation 1, we have, so what happens, p of x is equal to a to the power of x by x factorial divided by summation of k varies from 0 to n a to the power of k by k factorial. This is the first Erlang's distribution. That means if in the exam, if they ask you to derive an expression for first Erlang's distribution, you need to derive till here, that is enough. You need not to proceed. But if they ask you to derive till Erlang's last call formula, you need to go further. Okay. So this is the first Erlang's distribution, the probability of the last call, which is a grade of service, which is indicated by capital B, which is given by the symbol E of I1n of A, which denotes the loss probability for fully available group of n trunks offer traffic in Erlang's. So E of 1n of A. Okay. And in this equation number 3, the Erlang's last call formula, which replaces n is equal to n minus 1. So E of 1 comma n minus 1 of A is equal to, so now they are substituting n minus 1 in the place of n everywhere. So we have this one. Then therefore, so in equation 3, the Erlang's last call formula, where n is replaced by n minus 1. So E of A1 comma n minus 1 of A, here in everywhere in this equation number 3, we will replace n by n minus 1. So E of to the power of n minus 1 divided by n minus 1 factorial, and the denominator will remain same. So next, therefore, E of 1 comma n minus 1 of A into this one, we are taking the denominator this side, that is left hand side, so it will become like this. So in the right hand side we are left with only this. So after this we have, so we'll push this one to denominator. So the equation number 4 will be represented like this. Just arrangement of numerator to denominator, denominator to numerator, you will get like this. And we also know that by considering the summation of k varies from 0 to n, e of k to k factorial till e of n plus n factorial summation. So we have summation of k varies from 0 to n, a to the power of k by k factorial is equal to summation of k varies from 0 to n minus 1. We have a to the power of k by k factorial plus a to the power of n by n factorial. So similarly, if you take this part at the left hand side, we will be having like this. So at the right hand side, we will be having only this much of equation. So now this is equation number 5. By substituting equation number 5 in equation number 4, we have, so equation number 5 is substituted in equation number 4. Summation of k varies from 0 to n, a to the power of k minus k by k factorial minus a to the power of n by n factorial, which is equal to a to the power of n minus 1 by n minus factorial e of 1 minus n minus 1 of a. So now this part of left hand side is taken to right hand side. So the sixth equation will be represented like this. Now by substituting equation number 6 and equation number 3, we have e of 1 comma n of a is equal to a to the power of n minus 1, and this whole part is indicated here. Now we have divide the numerator and denominator by e of n by n minus 1. So both the things of numerator will cancel, and in the denominator with these two things will cancel. So we are left with 1 divided by 1 plus this whole thing is indicated as 1. So this is taken like this, and this one is taken like this, and this one is taken like this to rest. After that, this e to the power of n and a to the power of n is cancelled. I'll repeat this part again. After substituting denominator and numerator divided by a to the power of n minus here n and n minus n factorial, e of 1 comma n into a is equal to a to the power of n by n factorial, and this one both will cancel, and these things will cancel in the denominator, and in the numerator we're left with 1. And now by rearranging the denominator things, so this whole thing is indicated as 1 because both are cancelled, and this one is taken as it is, and the denominator part of this is taken upper, so it will become 1 divided by e of 1 comma n minus 1 of a, and this denominator is again reversed because it is at the denominator part, so it will become n factorial by a to the power of n. So now this if we split a to the power of n into a to the power of minus 1, so a to the power of n and a to the power of n will cancel. We're left with 1 plus 1 divided by a to the power of, since it is a to the power of minus 1, we will take it as 1 divided by a. So it will happen like this. So here n minus 1 factorial, n minus 1 factorial will cancel. So this n factorial is splitted as n minus 1 factorial into n. So this 2 will cancel. We are left with 1 plus n a into e1 comma n minus 1 of a. So we know that n factorial is equal to n minus 1 factorial into n. It's like how means 5 factorial means 4 factorial into 5. Okay, like that. So now 1 divided by a into e of 1 comma n minus 1 of a plus n divided by a into e of 1 comma n minus 1 of a. So now by rearranging this will go upper, so it will become a into e of 1 comma n minus 1 of a, n plus a into e of 1 comma n minus 1 of a. So this is the equation for iterative formula of Erlang's last call formula. So this is very important derivation, so you need to practice. So here lot of important stages are there, so you need to practice, and this is for 10 to 12 marks. So this is another example. A group of 5 trunks is offered 2 airlines of traffic. they're asking you to find the grade of service, probability that only one trunk is busy, probability that one trunk is free, and probability that at least one trunk is free. So what they're given n, that is 5 trunks, and how much traffic it is offering, that is 2 erlongs. So therefore a is equal to 2 erlongs, n is equal to 5. So the grade of service, considering Erlong's last call formula, we have b is equal to e of 1 comma n of a. So a to the power of n divided by n factorial divided by summation of k varies from 0 to n a of k by k factorial. We have k is 5, a is 2, so 2 to the power of 5 by 5 factorial. So it will become 32 by 120, and the summation of this whole thing will become this much. And finally we have, if you simplify, you'll get 0.037. So the grade of service is 0.037, and there is no unit for it. The probability that only one trunk is busy. For this is the first Erlang's distribution formula, that is P of x is equal to E of x by x factorial summation of 0 to n A of k by a k factorial. And we know that since it is only one trunk is busy, x is equal to 1, A is equal to 2 Erlongs, n is equal to 5. If you substitute, you will get 0.275 is the probability of one trunk is busy, that is P of 1. And next one, the probability that only trunk is free. So here the x will become 4. P of 4 is equal to 2 to the power of 4 by 4 factorial. Summation of k varies from 0 to 5 to the power of k by k factorial. If you simplify, you will get 0.0917. So next, last one, the probability that at least one trunk is free. So now, at least one trunk is free means probability of P of x is less than 5, which is equal to 1 minus P of 5, which is also equal to 1 minus B, 1 minus 0.037, which is also equal to 0.963. Okay, so this is about probability that at least one trunk is free, that is P of x is less than 5. Okay, so this is one more problem. Kindly practice it and calculate using calculators and check step by step the answer verification you do, because in the exam you may get confused how to do the simplification and all. So better practice you know your own with the calculator and verify the answers. So let me stop at this point. So today we discussed with Erlong's last call formula, Markov chain rules, and the problem which is very important. So we discussed about this four assumptions, that is last call systems. So this and all we have discussed this today. So the state transition diagram, how it is going to take this Markov chain, that and all we have discussed. I hope all of you understood today. Okay, kindly go through the things. If anything is there, let's discuss and we'll meet tomorrow. Thank you.